Kia ora Year 12. This is a question for Henry from the June 2020 Stats 2 paper, and it's question 4. Now, Henry's question was on part B, but I'm going to do the whole thing. You can't really do B without doing A, and then we might as well go on and do the hypothesis test that we've got in part D. So let's have a read first. We've got the score on one spin of a 5-sided spinner, and that's given to us by the random variable x, and this is the probability distribution table. So we've got the probabilities here, and we've got x here. So straight away, I'm asked to show that the variance of x is equal to 1.2. So for that, we need to put in our row up here of x squared values, so 0, 1, 4, 9, and 16. And I'm going to use the fact that the variance of x is equal to e of x squared minus e of x minus e of x all squared. That means that the first thing I've got to work out is what's the mean of the random variable. Now, I'm definitely going to need that for these bits down here anyway, so that's not a bad thing to do. So e of x will be this times this plus this times this and so on. So it's going to be 0, oops, what's happened? Okay, I had the OneNote weird glitchy thing. So I've got this times this, so 0 plus this times this, 0.2 plus these two together, 0.8 plus 0.6 plus 0.4. That gets me a mean of 2, right? The next thing in here is to show that the variance of x is 1.2. Oh, that's going to be a pain having that over there. Okay, let's do it here. So e of x squared is going to be this number times the probability and so on. So e of x squared is equal to 0 plus 0.2 plus 4 times 0.4 is 1.6 plus 9 times 0.2 is 1.8 plus 16 times 0.1 is 1.6. And that all adds up to give me 1.8, 3.6, 5.2. And that means that the variance of x is equal to 5.2 minus 2 squared, which gives me 1.2 as required. So far, so good. Okay, now this next bit reads a little bit weirdly. We're told that the spinner is now spun 200 times, and the score on each spin is noted, and the mean of the 200 scores is found. So we're going to want to work out the distribution of the sample mean. And we can do that using some of the results that we've got, but I'm going to do that quite slowly so that you see where that result is coming from. And then what we have to do is we're told that given that the probability that the mean is bigger than some number is 0.1, find the value of A. So the picture that I'm going to draw there is this one. So this is x bar. This is the distribution of x bar. The distribution of the sample mean is going to be centered on 1.2. And we want the probability that the sample mean is bigger than some number, that probability is only 10%. So we're going to want a number in this tail here. We're not going to work with x bar to start with. We're going to work with the standard normal distribution, which is z, and then we're going to translate that back to get a value of the sample mean. But first, let's figure out what this distribution of the sample mean is. So the expected value of the sample mean is going to be mu, which is 2. And the variance of the sample mean is going to be the variance of x divided by n, which is 1.2 on 200. But I'm going to show you how we can build that result up in case you have a freak out moment in the exam and you forget where it's come from. So think about what we're doing with these 200 throws. We're writing down each score and then we're finding the average. So the variance of x bar is equal to the variance of 1 over 200 times x1 plus x2 and so on up to 200. Right, so we've got a linear combination here, 1 over 200 times the sum of 200 things with variation. So it's going to be 1 over 200 squared times the variance of x1 plus x2 and so on. But we know that when we've got the sum of random variables, that as long as they're independent, we just sum their variances. So in here, we get 1 over 200 squared times the variance of x1, which is 1.2, x2, 1.2, and so on. And we've got 200 of those 1.2s. So it's 200 times 1.2 over 200 squared, which is 1.2 over 200. And that's where our result that the variance of x bar is equal to the variance of x divided by n comes from. Okay, so that was a detour, but Henry, I suspect that was one of the places that you were tripping up with part B, and that probably means that quite a few other people are also tripping up with part B. So let's go back into the question. It's here somewhere. And now that I know the distribution of x bar, we can do the rest of this problem. So x bar is distributed roughly, normally, with a mean of 2 and a variance of 1.2 over 200. We want the probability that x bar is greater than this magic number a to be 0.1. When we go to our z tables, what we're looking for in here is this value here that's cutting off 0.1 there. So we're saying phi of what will give me 0.9. And we can use the bottom part of that table. I'm just trying to see if I've got my normal table here. I've got the wrong bit of the normal table. Oh no, here we go. So I'm looking for this number here, right? I want 0.9 over here, and that's happening at 1.282. Now I've got to go back and find the page I was on. Right, there we are. So that z value is 1.282. So what I have to do is to translate that z value back into a value for the sample mean. We've got the probability that x bar is greater than a is equal to 0.1, and we've got the probability that z is greater than 1.282 is equal to 0.1. So what's my standard mean here, my standard normal? Well, z is equal to x bar minus the mean, which we know is 2, divided by the variance of x bar, which is this. And we're saying, when will we get that equaling 1.282? So if you think back to like AS questions about the normal distribution, here's my z, and I'm just translating that number there, 1.282, into that number about an x bar. So that gives me x bar is equal to 1.282 times this plus 2. And that gives me 2.099303, which is equal to 2.10 to 3 sig figs. Now let's go back to the question and see if that makes sense. Yep, it does. So that tells me that A is equal to 2.1, because what we're saying is the probability that x bar is greater than 2.1 is a very or reasonably low 10%. And if you think about why that is, it's that because we're taking such a big sample, my variance is really, really low. So it's 1.2 divided by 200, which is 0.6. I'm doing this slowly. I haven't done this before I made the video. 0.6 divided by 100, which is a very low 0.006. In other words, by averaging, we are getting an incredibly squished into the middle distribution of the sample mean, right? And it's centered on 2. And so having x greater than 2.1 is out here. So that answer that we had makes complete sense when you look at that being the variance, right? And so the square root of that is going to be your standard deviation. Okay, I think that's enough on that. So Henry, if that's not making sense, please send me another email, and anyone else who's not sure about that, let me know. Next question is an easy one marker. Did we need to use the central limit theorem in your answer to part B? Well, you might have noticed that I had a little approximately somewhere here. So x bar is going to be approximately normal, and it's approximately normal because we know that the variance of x is not at all normal, right? X is this discrete thing with 5 possible outcomes, right? So we have to say yes, and we need to say that it was necessary because X was not distributed normally. So it's not one of those cases where we don't know about X. We know for sure that X is non-normal. So the only reason that we can do a normal thing with the sample mean is that I've got a big sample size going on. So it will be roughly normal. Okay, now Johan has another similar spinner and he thinks it's biased so that the mean score is less than 2. So he does his spinner 200 times and he finds that the mean of the 200 scores is 1.86. So given that the variance on one spin of this is also 1.2, test his suspicion. Okay, so we've got to set this up properly. So H0, mu equals 2, H1, he thinks it's biased, mu is greater than 2, and we have to say mu is equal to the population mean score for his spinner. Right, it's not enough just to say that. You've got to say what on earth is this mu thing that we've worked out. Right, and we've got x bar is equal to 1.86. So we want the probability that x bar is that number or even weirder, given that the mean is equal to 2. So we're going to standardize that just like we did before. So that's the probability that z is less than 1.86 minus 2 divided by root 1.2 over 200. So how weird is my outcome here? We've got the probability that z is less than negative 0.1807. So there's my z picture. I'm down here. The normal table won't give me that, but it will give me this probability at 1.807, which actually is probably much further in the tail. So it's 1 minus phi of 1.807, which is 1 minus 0.9646, which is 0.0354. Now we have to compare that to the significance level of the test, which I think was 5%, but I've lost track. Oh, yep. We're testing at a 5% significance level. So to finish that off, what we're saying is that this result is very unlikely. So it's less likely than a 5% chance. So since 3.54% is less than 5%, we reject H0. There is enough evidence. I'll just say this instead of writing it down, guys. So there is enough evidence to conclude that the mean of the spinner is below 2 and that the spinner is biased downwards. All right, guys, thanks for watching. This was quite long. I'm not sure if anyone's still out there after nearly 13 minutes, but keep on sending in the questions. Henry, that was a really nice problem to go over. If you're in 13 MCA, I've done work solutions for the papers from this year, and I'm going to chuck them onto Google Classroom later on today.